Constellation-class frigate program was halted by the U.S. Navy after just 2 ships, with 4 additional hulls that had not yet begun construction officially canceled. Secretary of the Navy John Phelan delivered a famously blunt verdict. The frigate had reached 80% of the cost of an Arleigh Burke destroyer, while offering only 60% of the capability, making it economically irrational to continue. The design had been sold to Congress on the promise of 85% commonality with the proven Italian Frem hull, yet uncontrolled Americanization of the design left only 15% of the original parent design intact. This failure left the Navy with a 26-year frigate gap that had been growing since the last Oliver Hazard Perry-class ship left service in 2015. The answer was FFX, a new frigate based on the Coast Guard's Legend-class national security cutter, a hull already in serial production at Huntington Ingalls Industries with a proven track record of at-sea performance. FFX is split into 2 distinct variants, a concept that is itself a refinement of the patrol frigate proposal Huntington Ingalls had pitched years earlier before losing to Frem in the original FFGX competition. Flight 1 is a low-cost patrol frigate and containerized missile launchers, but no permanently installed vertical launch system, designed specifically for presence missions and low-threat escort duties. Flight 2, planned for the 2030s, will carry 32 Mark 41 VLS cells and a 3-phase fixed SPY-6 V3 radar, offering the higher-end combat capability that the earlier configuration lacked. The Navy envisions a total fleet of 50 to 65 FFX ships, with Flight 1 providing immediate relief to the overworked destroyer fleet, and Flight 2 eventually delivering a distributed lethality platform. This staggered approach is meant to rebuild frigate production expertise after a quarter-century gap, while de-risking the combat system in controlled increments. The National Security Cutter and FFX both use a CODAG arrangement combining 2 MTU 20V1163 diesel engines with a single General Electric LM2500 gas turbine. On diesel power alone, the ship cruises efficiently for long-range patrols, while the LM2500 kicks in to push the vessel to its maximum speed of approximately 28 knots. This is notably slower than other frigates using more modern MTU 20V8000 series diesels paired with the same LM2500 turbine, a combination that has demonstrated sustained speeds exceeding 30 knots on platforms like the French Frem. The choice to retain the older 1163 engines reflects the program's philosophy of minimal change to an existing hull, but it also permanently limits the sprint speed and power margin available for the electrical demands of modern combat systems. The diesel generators that supply ship service power are a separate matter entirely, and these may need significant upgrading to handle the enormous electrical appetite of the SPY-6 radar family. The most severe technical challenge facing FFX is electrical power generation and thermal management. The SPY-6 family of radars use gallium nitride semiconductor technology that delivers dramatically greater sensitivity than earlier systems, but demands at least twice the electrical power and generates enormous waste heat. The NSC hull was never designed for such loads, and even the Flight I variant with its lighter, rotating radar may push the electrical margin to the very edge of what the existing generators can sustain. When Flight II adds 3 fixed-face arrays and 32 VLS cells, the combined electrical and cooling load will almost certainly require a complete overhaul of the power plant, switchboards, and chiller systems. Without these upgrades, the frigates risk losing combat capability precisely when they need it most in a high-intensity electromagnetic warfare environment, where systems must run continuously without throttling. Weight growth is a specter that destroyed the Constellation class, and it haunts FFX from the very first hull. The NSC was built to commercial standards with modest stability margins, never intended to carry heavy missile cells embedded deep in the bow, or massive radar arrays mounted high on the superstructure. Adding even the Flight I combat systems, including the 57mm gun, ram launcher, and containerized missiles, already require substantial reballasting and leaves almost no service life growth allowance for future upgrades. When Flight II introduces 32 strike-length Mk-41 cells and the heavier 3-face fixed radar, the hull will likely exceed the center of gravity limits that the original designers intended. If the Navy permits even modest additional requirements during construction, the program could replicate the exact sequence of weight creep, stability erosion, and redesign that made Constellation unbuildable at any reasonable cost. Lockheed Martin is the combat system integration agent for Aegis Baseline 10, the first version of the Aegis combat system designed to integrate the Spy-6 radar family natively. However, no frigate-sized platform has ever hosted this software-sensor combination, and the integration challenge is substantial. The Navy operates land-based test sites at Morristown and other locations, but no dedicated land-based integration facility for the frigate-specific power, cooling, and electromagnetic environment has been publicly funded. Without rigorous shore-based testing, the first Flight I ships will become de facto at-sea test platforms, discovering software bugs and hardware incompatibilities only after commissioning. That approach risks years of post-delivery rework and could delay the operational capability that the fleet urgently needs. The integration risk is even higher for Flight II, which packs more demanding systems into the same constrained hull architecture. Industrial capacity may be the single greatest threat to the entire FFX enterprise, dwarfing even the technical challenges. The Navy estimates that 250,000 additional skilled shipyard workers are needed across the next decade, yet the current workforce is aging rapidly, with a quarter eligible for retirement within 5 years. Welders, pipe fitters, electricians, and ship fitters require years of apprenticeship to reach proficiency, and competition from the construction and energy sectors makes recruitment persistently difficult. Meanwhile, the same shipyards that would build FFX are already saturated with Arleigh Burke destroyer production, Virginia-class submarine construction, and amphibious ship overhauls. Every frigate slot on the production line consumes dry dock space, skilled labor, and supply chain capacity that could otherwise be used for a high-end combatant, creating a direct opportunity cost that the Navy has not yet fully accounted for. Building Flight I before Flight II is a deliberate risk management decision rooted in industrial and operational necessity. The deliberately simplified design allows Ingalls Shipbuilding to relearn frigate construction on a build-to-print hull with minimal changes, training a new generation of workers who have no living memory of the Oliver Hazard Perry class production line. Operationally, Flight I vessels can immediately assume low-threat missions such as counter-piracy, maritime security patrols, and anti-submarine scouting that currently waste the 96-cell VLS capacity of expensive Arleigh Burke destroyers. That operational relief alone is worth the investment, because it preserves the high-end fleet for high-end combat in the Pacific theater. Simultaneously, Flight I vessels will gather real-world data on how the NSC-derived hull handles the Aegis combat system at sea, feeding lessons directly into the final Flight II design. The Navy has placed a significant bet on modularity, emphasizing containerized missile launchers and mission bays that can accept new payloads without lengthy shipyard availabilities. In theory, a Flight I hull could later be upgraded with additional VLS cells or a towed array sonar by swapping standardized containers on the aft mission deck. In practice, however, retrofitting a deep magazine vertical launch system into a hull not originally designed for it is a massive structural undertaking that may rival the cost of building a new ship from scratch. The distinction between Flight I and Flight II is therefore not merely a software or sensor difference, but likely requires different structural foundations from the keel up, effectively making the two variants separate production baselines. Without engineering growth margins deliberately incorporated during initial construction, the promise of modularity may prove as hollow as it did for the littoral combat ship program. Any assessment of FFX must be calibrated against the accelerating modernization of the People's Liberation Army Navy. China's Type 054B Jiangkai-III frigate is a 6,000-ton warship equipped with a 32-cell vertical launch system, a dual-face rotating AESA radar, and a comprehensive anti-submarine warfare suite, including both bow-mounted and towed-array sonars. 4 hulls are already in service or advanced construction, and Chinese shipyards at Hudong Zhonghua and Huangpu Wenchong are shifting towards stable serial production. In a direct engagement, a Flight 1 FFX lacking any permanently installed VLS would be severely outmatched by the Type 054B's anti-air and anti-surface missile loadout. Even Flight 2, when it finally arrives in the 2030s, will be qualitatively comparable at best, while the Chinese frigate fleet will likely have grown to 30 or more modern hulls by that point. The most sobering statistic in the naval balance is not weapons loadout, but industrial capacity. Chinese shipyards are estimated at roughly 23 million tons of production capacity compared to less than 100,000 tons in the United States. This staggering 200-to-1 advantage means China can sustain combat losses and replace them faster than American yards can build new hulls in peacetime, let alone under wartime conditions. The US plan for 50 to 65 FFX ships over 2 decades may sound ambitious, but by 2035, the plan could deploy a frigate fleet 2 or 3 times that size. In a high-attrition Pacific conflict, the side that can outbuild its losses holds a decisive strategic advantage that no single ship quality can overcome. The current FFX production rate does not close this gap, it merely slows the rate at which the gap widens. The undersea threat is the silent dimension of the frigate problem that receives less public attention than missile counts. China is building both diesel-electric and nuclear-powered submarines at a pace that directly challenges US undersea dominance, with intelligence projections forecasting approximately 80 submarines by 2035. An effective frigate must therefore be a credible anti-submarine warfare platform, yet the Flight 1 FFX has no hull-mounted sonar, and its towed array system remains unfunded. The embarked MH-60R helicopter provides a mobile sensor, but only within a limited radius of the ship, leaving the vessel itself acoustically deaf to quiet modern submarines operating at tactically relevant ranges. If Flight 2 does not incorporate a full ASWX suite with both active and passive sensors and a propulsion quieting design, the US frigate fleet will be a liability in precisely the mission set for which it is being built. The other half of the Navy's surface force plan is the Trump-class battleship, or BBGX, a massive 40,000-ton arsenal ship carrying 128 VLS cells, hypersonic missiles, and megawatt-class directed energy weapons. While such a capital ship provides overwhelming offensive firepower, a fleet architecture built around a handful of BBGX and a thin frigate layer recreates the low-density, high-value problem that already makes aircraft carriers acutely vulnerable in contested waters. The loss of even a single BBGX in combat would remove more missile capacity than the loss of 4 Flight 2 frigates, creating a catastrophic single point of failure for the entire task force. A force that distributes lethality across a larger number of capable mid-range frigates is inherently more survivable and operationally flexible than one that concentrates it in a few supremely powerful but scarce platforms. The high-low mix works only if the low component is numerous enough to afford losses. The two-flight FFX strategy is intellectually honest about its own limitations in a way that previous programs were not. It prioritizes speed and numbers over theoretical perfection, freezing the Flight 1 design early and deferring high-end systems to a later variant that can benefit from real-world lessons. Yet, the cycle of requirements creep that destroyed Constellation is deeply institutionalized in Navy acquisition culture and cannot be wished away by good intentions. The same political pressures, fleet-driven capability demands, and industrial lobbying that turned FREM into an unaffordable Frankenstein can easily re-emerge on the NSC hull. If Flight 1 is permitted to accumulate incremental modifications during construction, or if Flight 2 is burdened with every conceivable future weapon system, the program will die the same death as Constellation, only at a slower and more protracted tempo. FFX represents the most viable path the U.S. Navy currently has to regain a frigate fleet within a relevant timeframe. It is a pragmatic, risk-managed attempt to use an existing hull to deliver ships quickly, rebuild industrial expertise, and relieve the overstretched destroyer force. But it is not a decisive solution to the broader strategic challenge. The technical risks of the NSC conversion are genuine and unresolved. The workforce shortfall is chronic and deeply structural, and the Chinese production machine is not waiting. By the mid-2030s, the United States will likely possess a modest frigate fleet capable of presence and lower threshold missions, while the PLN will field a larger, increasingly capable force that can sustain attrition and project power. Whether that outcome proves strategically acceptable depends entirely on whether the Navy uses the time bought by Flight 1 to invest in a true next-generation combatant, and whether Congress funds that transition before the frigate gap becomes an irreversible fleet-wide crisis.